Hello, my name is Célia, and I'm going to be talking about the analytical solution of the diffusion equation and phase transition in Hamiltonian mappings. This presentation is organized in this way. The studied mapping is described by two variables, action and angle, and two control parameters, epsilon that controls the nonlinearity of the system, and gamma that controls the divergence of the angular variable when the action is small. When it's small, there is no correlation between these variables, then the sign function has random behavior. This brings the diffusion of the orbits in the phase space. And when the action increases, there is the correlation between these variables that brings the regular orbits in the phase space. And when we calculate the determinant of the Jacobian matrix of this system, we have that it is equal to 1. So this is a conservative system. Here we have the phase space of this mapping considering gamma 1 and two values of the parameter epsilon. When epsilon is 0, we have just regular orbits in the phase space, and when it's different from 0, we have the coexistence between chaotic C, periodic islands, and invariant curves. Here in blue we have the first invariant spanning curves, positive 1 and negative, and they limit this chaotic C not diffuse and bounded. So if it happens, the Liouville theorem would be violated, and the location of these curves are described by these expressions. The observable that defines the root mean squared is given by this expression in 2. The first average is over the ensemble of initial conditions, and the second one is over the orbits. When we plot this expression, we have this behavior, and from this we can propose this scaling hypothesis. And these critical exponents can be related by this scaling law. The diffusion equation is used to describe the particles in the chaotic C because their behavior is similar to the random walk. Here, P is the probability to find a particle with an action 9 in an instant n, and D is the diffusion coefficient defined by this expression. As boundary conditions, we have there is no flux on those first invariant spanning curve, as I said before, and initial conditions are described by the direct delta function. We use the separation of variables method and obtain this expression for the I-root mean square. And we plot this expression here in the continuous lines, and the symbols are the simulations. We have here the good agreement between them, and when we consider these transformations, we overlap all those curves onto an universal one. We have here scaling invariance, and because of the scaling invariance, we can talk about the phase transition. The Birkin symmetry is identified by the control parameter epsilon, and we change its value. We have the change in the phase space. The other parameter can be characterized by the variable that describes the dynamics. So the I-root mean square would be a candidate to it. When we apply the limit when epsilon goes to 0, it approaches to 0 too, so it's not a good candidate. So then we consider the susceptibility. It's given by the partial derivative of I-root mean square with respect to epsilon. Then when we apply the limit when epsilon goes to 0, it diverges. So we have here, this is the candidate to the order parameter. This is the order parameter, and we are facing a second order phase transition. The elementary excitations are defined by this function. As I said before, when the action is small, this function has a random behavior. This brings the diffusion in the orbits. So the elementary excitations are defined by this expression. And the topological defects are related to the stiffness effects. It happens when the particles are trapped temporarily in center regions in the phase space. So we studied the bidimensional map described by two variables and two control parameters, and characterized the diffusion using phenomenological description and the diffusion equation. We confirmed the phase transition and conclude it is a second order phase transition. And we have here the main bibliography used in this presentation, and these results were supported by these Brazilian agents. So thank you for your attention.